Let's consider a horizontal plane somewhere in the subsurface, well below the surface. We're going to balance the vertical forces that this horizontal plane would see in the subsurface. So pushing down on this, of course, is the weight of all the soil that goes and sediments that go up to the surface. So you can imagine a prism of a column of sediments and water above this plane. We would call this the total stress pushing down on this plane. Holding up this plane are two components. One is the pore pressure of the fluid that would be in a porous medium in which this plane is situated. The other is what we call effective stress. So these all take a little bit more explanation than the total stress above. So sigma t is the total stress from the overburden. P is the pore pressure. So this is just the pressure of fluids in the pores. So if we have some grains of sand, the pore pressure is the fluid that's in those pores, and it's holding those grains apart. The effective stress is the stress of all these grains pushing against one another. And you could think of that as sort of being a grain skeleton. So that is the stress of all these grains sort of pushing against one another and holding each other up, right? So this is in equilibrium. This system has to be in equilibrium or else this plane would accelerate up and down. So let's look at a force balance. On the plane. So pushing down, we have sigma t. Now remember, a stress is a force per unit area. So because we're talking about force, I'm going to go ahead and multiply times the area of this plane. So pushing down is the total stress, and then pushing up is the effective stress plus the pore pressure, all times the area of that plane. Okay? So obviously the areas go out, so we don't have to work with the areas, but if we want to start off talking about force, we have to talk about the stress, which is force per unit area, times the area over which it's applied. So since the force is pushing down, the force is pushing up, are all applied to the same area, we don't have to worry about the area. We can also look at the change in stress. So we could write the change in the overburden stress is equal to the change of the effective stress plus the change in the pore pressure. And I'm using the derivative d to talk about the change. Okay. So what does this say? This says that if the total overburden stress doesn't change, meaning that no sediments are removed from the top of this plane or dug down from above, then if this doesn't change, then the sum of the changes of these two have to be the same, which means that if you drop the pore pressure, the effective stress has to go up, and if you reduce the effective stress, the pore pressure has to go up. So let's take a look at the case where this is 0, and it's 0 because the overburden doesn't change. So if we were to consider the bottom of an excavation, for example, this would not be the case. But in this particular case, we can say that the change in the effective stress is equal to the negative of the pressure, which means that as the pressure increases, we have a negative here, and then the effective stress has to decrease. So now we have this relationship between our effective stress and our pressure, But we don't like to work in pressure. We like to work in hydraulic head. So let's recall our definition of static hydraulic head, which is simply H is equal to P over gamma plus Z. You should know that pretty well by now. And we can also write this in a derivative form so that the change in pressure plus the change in elevation is equal to the change in hydraulic head. Now notice that this change in elevation actually is 0 in this case because we have a horizontal plane. So that means we can solve for dP, which is just simply gamma times the change in H. And now we can substitute this back into our equivalency between effective stress and the pore pressure. And now we have that in terms of hydraulic head. So this expression that relates the effective stress and the hydraulic head is going to turn out to be important, because what it's suggesting is that when the head decreases, the effective stress increases, and that increases this stress between these grains. It's going to cause them to try to collapse. And so this is going to be important when we start thinking about things like subsidence due to water withdrawal and sliding in landslides, when we have an increase in head that reduces that effective stress and reduces the friction of those grains.